All right, so next up, we're going to talk about the different kinds of solids, the four different kinds of solids, and then also liquids. So again, we should already know that our definition for a solid is anything that has a definite shape and volume. And solids have a definite shape because they have attraction between those particles that keeps them from moving around. Really, they just vibrate around fixed positions, those particles. Whereas those particles are also very, very close together. And since they're really close together, at a significant amount of pressure, whether you apply it or reduce it, won't really change the volume of that substance significantly. The reason you could change the volume of a gas is because the particles were really, really far apart to begin with. You could push them closer together. So attraction holds them together, keeps them close together, and keeps them from moving. Right? If they can't move, then you're going to have that definite shape, right? Moving freely, that is. Remember, they do vibrate around fixed positions. Otherwise, again, they're really close together, so you can't push them any closer together, but also they're not going to go apart from each other because they're attracted to each other. So that's where we have that definite volume that comes into play, right? The volume will not change based off of the pressure you apply to that solid. But otherwise, there are four different kinds of solids, and we're going to talk about each. First up is ionic solids. And ionic solids are held together by ionic bonding. They form regular crystals. So a good example of this would be salt. And when I say salt in this case, I mean table salt. We'll talk about salt later as being an actual generic term, meaning a product of an acid-base reaction. So sodium chloride happens to be a salt, but it's not the only salt. But anyway, right, that compound is ionic, meaning that I have ions, positive sodium ions. Again, we should already be aware of that. And negative chloride ions, and those ions are attracted to each other. And those attractions are called ionic bonds, right? That's an ionic bonding. So if I have a sample of sodium chloride, I don't just have one sodium, one chlorine. I have thousands and thousands, if not millions and millions or billions and billions of those sodium ions and chloride ions. And so they all just arrange themselves so that that attraction is always there. So if I have any given sodium ion, it should be surrounded by chloride ions and vice versa. So you end up making this structure that's regular because you always have to have attractions, positives to negatives, and negatives to positives, right, all throughout the solid. Now, I drew a 2D version of this. Remember, there's actually, for each of these central ions, so if I'm looking at this chloride ion here, or this sodium ion here, there should actually be, for the chloride, a sodium out in front of the screen that you're looking at, and also a sodium back behind it, because it needs to be surrounded by those sodium ions. So it's actually going to be surrounded by 6 sodium ions, whereas that sodium on the right is surrounded by 6 chloride ions, and every ion is surrounded by 6 other ions at opposite charges. So that leads to a specific structure, a regular crystalline structure, again, that results from those positive and negative charges. If you have different compounds, they have different crystalline structures. Because remember, if this happened to be a calcium chloride, I'd actually have 2 chloride ions for every calcium ion, and that changes the way that they arrange themselves. There'd be so many more chloride ions that you can't really do it the same way that you did with the sodium chloride. So we're not going to really talk about all of the different specific crystalline structures, right? Because there's lots of geometric patterns that can occur. But in the case of the salt, since it's 6 around 1, that 6-sided shape that appears happens to be cubic, right? Whereas for the calcium chloride, you get something different. So we don't really worry about that. We just want to know how these things are attracted to each other and what this structure looks like. We're going to talk more in class as to how to identify the different kinds of solids, but one of the only things right now we want to be concerned with is understanding that if I was to hit this substance with a hammer, right, it would likely shatter. So ionic solids are said to be brittle because if I shift this structure, all these attractions that I had turn into repulsions. Right? If I take this chloride here and move it down to where this sodium is, right, now it's not next to a sodium ion anymore, it's next to this other chloride ion. So one's going to repel the other. And then this sodium is going to be next to this sodium, and you keep doing that on down the structure. If you cause a shift in any one of these lines, right, if you create a fault line, right, all these attractions turn into repulsions. So if you shift it a little bit, it just all breaks apart. So they're very brittle for a reason. Right? Otherwise, there's other specific properties for ionic compounds that we'll talk about in class. Molecular solids, on the other hand, are held together by a variety of intermolecular forces. If bonds are strong, you should have crystalline structures, so you can have snowflakes. Again, we talked about water attracting other water molecules. If you have ice, if you have that water and in a solid form, if you have ice, you're going to have a crystalline structure because of the same thing we just talked about. But this time I don't actually have ions, I have water molecules that just happen to be very polar. But because of the shape of those water molecules, because they're bent, I can't get a very regular structure out of this. Because I know that oxygen has to be next to hydrogen. See, it's supposed to be black. This doesn't want to change. There we go. I know that oxygens have to be next to other hydrogens so that I can create those attractions. And again, in a, excuse me, I'm drawing all sorts of crazy things here. Let me just fix that. Get rid of those black marks. So let me finish the picture and then talk about it. I have to have this hydrogen next to this oxygen for that attraction to occur, but those molecules can twist and turn, and it creates a lot of different possible structures for that ice. So again, you've heard that there's no two snowflakes that are alike. That's because of the way that this molecule arranges itself. So again, it was easy for that ionic compound on the last slide to arrange itself in a regular crystal because every sodium had to be surrounded by chlorides. But the same thing's kind of true here. It's just not a regular shape because the water molecule itself, again, it's a molecular solid because I have molecules that are attracted to each other. They just happen to be polar molecules in this case. Right? If it's a strong bond, it's going to be some kind of polar interaction. It's a dipole-dipole. It's a hydrogen bond in this case. That's how you end up with this crystalline structure for that specific compound. But if they were London dispersion forces, you'd actually end up with some sort of amorphous solid as opposed to being a regular crystalline structure. You might have something more like a wax that actually can be shaped and molded, right? So when we talked about that carbon compound and the intermolecular forces, with all those little forces that added up, right, those forces are still little, so it's pretty easy to break them. But that solid becomes amorphous as a result. Network solids, these specifically are essentially giant molecules. So you have something big enough that you can see it, but every atom's connected to every other atom. Right? So our example for this one is like a diamond. Right? So a diamond actually has carbons connected to other carbons. The only things in a diamond are carbons. but they're all connected to other carbons, and it just grows bigger and bigger and bigger to make this huge structure, this huge superstructure. And since those attractions between particles here are actual covalent bonds, which are stronger than ionic bonds, which are stronger than those polar interactions from the last slide, right? And or those London dispersion forces. So they're stronger than the attractions between atoms and particles in these last two slides. You're going to end up with a very strong structure, right? So you know that diamonds are very, very hard. Kind of hard to break. If you hit it with a hammer is more likely to break than the diamond, right? Or at least if it's a real diamond and it doesn't have any imperfections in it. So don't just be hammering on diamonds later on. They're kind of expensive, so you wouldn't want to break them. But they are very hard substances for a reason. We use diamond tip saws to cut through other very hard substances because they're so strong. But again, every atom is covalently bonded to another atom. So they become very strong because of that. And then finally, we have metallic solids. Right? These are different than the others because metallic structures have this sea of electrons that we like to talk about. So essentially, you have these atoms. So if I have an aluminum bottle or can or whatever, I have this metal, right? All those aluminum atoms in my solid have these 3 valence electrons that they really don't want. Metals tend to lose electrons in reactions, and therefore all these aluminums have 3 electrons surrounding them, but they don't really want those electrons, so those electrons don't stay put. They actually start traveling throughout the entire solid. And this is happening for each one of these aluminum atoms. They have electrons around them that don't stay around them. They just keep passing them back and forth from one atom to the next. All the aluminums themselves, right, without their electrons, have this apparent charge that's positive, right? The aluminum ion particles that exist in this structure all have a +3 charge. But those 3 electrons that are associated with each atom just keep moving, right? It's like a game of hot potato. They're just going from one atom to the next. None of those electrons stay associated with the original atom that they were part of, which is where you get this weird structure. But that structure has very specific properties, right? Metals are good at doing a lot of different things. They're very conductive, right? Electricity is a stream of electron-like particles. So it's very easy to understand why this metal could conduct that electricity. Electrons are already freely moving throughout the solid, so conducting electricity is really easy. Right? They're also very malleable and ductile, because as long as that aluminum ion doesn't leave that sea of electrons, it's still going to be held together with the rest of that solid by that sea of electrons that continually surround it. Right? One of the analogies I like to think of for that is it's kind of like you have this chunky peanut butter. You have these peanuts that are floating around in the peanut butter itself, but they don't fall out of the peanut butter. But you could move them around all you wanted. You could push on them and pull on them. As long as you didn't break them out, if you didn't pull them out of the peanut butter surrounding them, the solid's gonna stay together. So again, we got these 4 different types of solids. We want to know the difference between each type of solid, and we are going to go through each thing specifically, what kind of specific properties help us identify these solids in class. But otherwise, understand the basics for each one. That's what this video is for.